Initially, there was an infinitely dense mass of matter. This primordial point, often described as a singularity, was a state of unimaginable pressure, temperature, and energy, a state beyond comprehension. From this incomprehensibly dense origin, an event occurred that would forever alter the course of everything, the Big Bang. This wasn't an explosion in space, it was the expansion of space itself. With it came the release of intense energy and radiation, giving rise to the birth of atoms, molecules, stars, and galaxies. From nothingness came complexity. From silence emerged the symphony of creation. This expansion was not a chaotic outburst but an intricately governed process driven by the laws of physics, laws that, ironically, also emerged from this very birth. As the universe grew, it cooled, and in its cooling, it allowed particles to combine, form hydrogen and helium, and eventually coalesce under gravity to ignite the first stars. These first-generation stars forged heavier elements in their cores through nuclear fusion. When these stars ended their lives in violent supernovae, they seeded the cosmos with the building blocks of planets, moons, oceans, and ultimately, life. Scientists have long relied on the redshift of light from distant galaxies to study this cosmic expansion. The further away a galaxy is, the more its light is stretched, shifted toward the red end of the spectrum, by the expansion of space. Edwin Hubble's groundbreaking work in the 1920s confirmed this. His discovery that galaxies are moving away from us laid the foundation for the Big Bang model. Yet, while this model has offered a compelling narrative of the universe's beginning and its ongoing expansion, it does not explain everything. Particularly, it fails to address what came before the Big Bang or what lies beyond the boundaries of our observable universe. Some physicists propose that the Big Bang wasn't the absolute beginning. In fact, recent cosmological theories suggest that our universe might be part of a larger, eternal cycle, a series of expansions and contractions, births and deaths of universes in an ever-recurring cosmic rhythm. Known as the cyclic universe, or the Big Bounce theory, this concept challenges the very notion of a singular beginning. According to this theory, the universe undergoes an infinite series of Big Bangs and Big Crunches. In each cycle, the universe expands from a dense state, evolves for billions of years, and then contracts again due to gravitational attraction, eventually collapsing back into a singularity. From this collapse, a new universe is born in another Big Bang. The process continues eternally. This view provides a fascinating alternative to the conventional Big Bang narrative, offering an explanation for the apparent fine-tuning of the universe. If universes are born and reborn in infinite cycles, it's not surprising that one like ours eventually came to exist, with just the right conditions for life. Adding weight to this possibility, the cosmic microwave background, CMB, the faint afterglow of the Big Bang, has shown certain anomalies that some scientists interpret as evidence of past universes. Small, unexplained temperature fluctuations and patterns in the CMB might hint at pre-Big Bang activity or imprints from a previous cosmic era. While this interpretation remains controversial and debated, it fuels the growing suspicion that our universe may not be the first, nor the last. Other models propose a multiverse, where countless universes exist simultaneously, each with different physical laws and constants. In this framework, our universe might be just one bubble in a vast cosmic ocean, occasionally colliding with or branching off from others. Some versions of the inflationary model, a refinement of the Big Bang theory that describes a period of rapid exponential expansion in the early universe, predict this kind of multiverse. During inflation, quantum fluctuations could cause pocket universes to form, each emerging from its own local Big Bang. These parallel universes might never interact with ours, making them nearly impossible to observe directly, but the mathematics behind them is increasingly The concept of cyclic universes also appears in ancient traditions and philosophical schools. For example, Hindu cosmology describes time as cyclical, consisting of vast epochs called yugas, with the universe undergoing creation and destruction in repeating cycles. While these ancient ideas lack the empirical backing of modern physics, the similarity in structure is fascinating and highlights humanity's age-old struggle to comprehend the cosmos. One of the most intriguing modern proposals is the ekpyrotic universe model, inspired by string theory. It suggests that our universe originated from a collision between higher-dimensional brins floating in a larger dimensional space. Each collision gives rise to a Big Bang and a new universe. In this picture, the universe doesn't begin from a singularity but from the gentle touch of multidimensional structures. Over time, these brins are pulled back together by gravity, and another collision occurs, spawning a new universe. This process can, theoretically, continue forever. These theoretical ideas remain difficult to test. The nature of time, space, and the limits of our observable universe make it extremely challenging to find definitive evidence for what came before the Big Bang, or if there even was a before. Our scientific instruments and telescopes can only see so far, and beyond that, we enter the realm of speculation guided by mathematical models and logic. Yet, some scientists believe that gravitational waves, ripples in spacetime caused by cataclysmic cosmic events, could one day carry imprints from before the Big Bang. If we could detect patterns in the cosmic gravitational wave background similar to how we study the CMB, we might uncover hints of a pre-existing cosmos. The James Webb Space Telescope and other next-generation observatories are stepping closer to this frontier, peering deeper into space and further back in time than ever before. One of the most revolutionary ideas in theoretical physics is that time itself may be an emergent property, not something fundamental, but something that arises from more basic quantum processes. If time can emerge, perhaps it can dissolve and reform as part of a greater loop. Quantum gravity theories like loop quantum cosmology propose that the Big Bang was actually a bounce from a previously contracting universe. This model removes the singularity and replaces it with a smooth transition between cycles. In this sense, the Big Bang was not a beginning but a transformation. There are philosophical implications as well. If the universe is eternal and cyclic, then the question of a first cause becomes irrelevant. There is no starting point, no origin that needs an external cause. Instead, the universe simply is a perpetual engine of creation and collapse, with no ultimate beginning or end. This view challenges both religious and scientific worldviews that rely on a linear timeline and a singular genesis. While the cyclic model and its variants are still theoretical and require more empirical support, they open exciting pathways in cosmology. They encourage us to move beyond the idea of the Big Bang as the ultimate explanation and to explore deeper patterns in the fabric of reality. They also suggest that the death of our universe may not be an end, but merely a step in an endless cosmic cycle. As we look into the depths of the cosmos through telescopes and equations, we are not just looking outward, we're reaching for the deepest truths about our own existence. Are we a fleeting spark in a cold, indifferent universe? Or are we part of an eternal rhythm, one verse in a cosmic song that has no beginning and no end? The search continues. And with every new discovery, every faint signal from the edge of time, we inch closer to understanding not just how the universe began, but whether it ever truly began at all.